Hello, advanced chemistry students. This is Dr. Rogalski. This will be the final chapter for the year. We will be looking at chemical equilibrium, and we will take a little bit of time to look at acid-base chemistry. So chapter 17 will be chemical equilibria, and we'll also have a few slides here on an introduction. So we will also be looking a little bit at acid-base chemistry, and that will wrap up the long-distance learning year for 2020. Okay, there are a number of online resources. Bozeman Science has a good deal of videos you can watch, starting with lecture 62 going all the way through 67, 70, and 71. I have also put in the long distance learning folder YouTube links to the con videos for this unit as well. So there's a lot of resources available. Okay, so what is equilibrium? When we think of equilibrium, we think of a sort of balance. And in terms of a chemical system, equilibrium means that we have something very specific. It says that the forward rate is equal to the reverse rate. So we just finished a unit on kinetics. So when the forward rate is equal to the reverse rate of reaction, then we would say that the system is in an equilibrium state. Some examples of a system in equilibrium would be if you have ice cubes and water, where the ice cubes are melting. You have a reversible phase change taking place. If you own some of the sunglasses that respond to sunlight by changing color and then change back when you're inside, that's also a reversible photochromic process. Rechargeable batteries are another example of reversible processes, in this case electrochemical system. You use up chemical energy and then you replenish it using electricity to restore the chemical energy. Many biological reactions within our bodies are reversible processes. For instance, the transport of oxygen and the removal of carbon dioxide by our hemoglobin in our blood. And finally, the periodic tables that you were given at the very beginning of the course are heat sensitive, and they are reversible as well. You can touch it and it changes color, and then when the heat source is removed, it goes back. So all of these are examples of reversible processes which can achieve what we call an equilibrium state. So in the last unit we studied kinetics. That applies to the speed or the rate of a reaction, how fast the concentration of product appears, or how fast the reactant disappears per unit time. So in kinetics, we're asking how fast. In equilibrium, the question is, to what extent does the reaction go? What is the yield? And in other words, how much of a product is made? And there are two things we want to remember, that at equilibrium, the rate forward is equal to the rate reverse. It's one key element in the idea of equilibrium. And the other is that when delta G is equal to 0, the system is also at equilibrium. There's no driving force one way or the other that pushes a reaction to spontaneously move in one direction or the other. So at equilibrium, delta G is equal to 0. We call this system at equilibrium. It is a dynamic system on the molecular level. In other words, even though the forward and reverse rates are equal, it doesn't mean that everything's stopped, okay? It simply means that for every A that goes to B, a B goes back to A. So there's no net change in the observed concentrations. And keep in mind that it simply means that for every A that goes to B, a B goes back to A. That's the idea behind a dynamic equilibrium. So another way of thinking about it is that an equilibrium is a state in which there are no observable changes as time goes by. So for instance, if you are looking at a colored reaction, or a reaction that produces a color, as you observe the equilibrium, you're not going to see any changes in that. Again, we've already talked about this. Dynamic equilibrium, rate of forward and reverse are the same. Another important point, though, is that the concentrations of the reactant and product remain constant, but that does not mean that those concentrations are the same values or have the same magnitude. They may be very different and be in equilibrium. So in this slide, we see two pictures. One is ice cubes melting in a glass of water. That represents a physical equilibrium. We're observing a phase change. And the other is an example of a chemical equilibrium, where we have dinitrogen tetroxide, which is colorless, decomposing. So this is a decomposition reaction. So dinitrogen tetroxide produces nitrogen dioxide, which is brown. So you can actually observe the process of the system equilibrating by watching the change in color. And that's done in this glass vial. Okay, and so this is another example of the equilibrium process. It's the same reaction that we saw before. So again, we're starting off with the colorless substance, which is N2O4, dinitrogen tetroxide. So in the very beginning, we have mostly all reactant. And given some time, we're producing nitrogen dioxide, or the product. And the system continues to establish equilibrium, and as we see, there was one NO2 here. There's 3 NO2 in this picture. We have 1, 2, 3, 4, 5 NO2 in this picture. 1, 2, 3, 4, 5 in that picture. So what has happened in this between these two molecular scenes is that the concentration of NO2 is constant. So we can assume that we have achieved a chemical equilibrium. Okay, so that's what a chemical equilibrium might look like. One of the first things that we learn how to do in studying chemical equilibria is to learn how to write the equilibrium constant expression. There are a set of rules for this, and we'll run through them now before we practice. The concentrations of the reacting species in the condensed phase are expressed in molarity. So just recall molarity is equal to moles per liter. In the gaseous phase, the concentrations can be expressed in molar or atmospheres, or some other appropriate unit for pressure. The concentrations of pure solids and pure liquids and solvents do not appear in the equilibrium constant expression. They are counted as a 1. So they enter the equilibrium expression as a 1. And therefore they don't actually show up. And we view it this way because their concentrations are changing ever slightly. Excuse me, let me erase this. Okay, so concentrations have negligible changes. Okay, so that's why pure solids and pure liquids and pure solvents don't appear in the equilibrium expression. Their concentrations change negligibly, so we don't include them in the expression. The equilibrium constant, which we refer to as big K. So here's a different K in chemistry. It's a large K. The equilibrium constant has no units. So whereas we were very concerned about units in the last kinetics chapter, we're not worried about units for the equilibrium constant. However, in quoting a value for the equilibrium constant K, you must always specify a temperature, and you must also have a balanced equation. So those are two very important things in describing an equilibrium value. And the reason for the temperature being important is that the equilibrium constant becomes basically a ratio of rates of reaction. And we know from the kinetics unit that temperature affects rates. So that's why temperature is very important in establishing an equilibrium constant. So in terms of looking at how we write the equilibrium expression, if we have a general equation here, A and B are the reactants, M and N are the coefficients for them, and we have P and Q are the products, and S and R are the coefficients for them respectively as well. Okay, so when we write the equilibrium constant expression, we start with writing K, and you don't have to really worry about writing the EQ subscript, but K is equal to the product concentrations, and in this case the exponents are the coefficients of the balanced equation. We have products, this is very important, we have the products over the reactants. So here's reactant A and B, here are the coefficients from the balanced equation. So products over reactants. This is one of the things that students mix up in this kind of problem. You need to make sure you've got products over reactants, and you can't forget the coefficients becoming the exponents in this expression. So also the equilibrium constant is a constant that only changes with the temperature. So that's something important to remember as well. Okay, well, we'll start off with one of the more simpler types of equilibria that's called a homogeneous equilibria. That simply means that the reactants and products are present in the same phase. So everything's a liquid or everything's a gas. That's what homogeneous means. We can start with a reaction. Right here we have a reaction, and this is acetic acid. Acetic acid is a component of vinegar. It is reacting in water, so acetic acid is present in water. And when we talk about equilibria, we talk about a forward and a reverse reaction. So when you write these kind of expressions, you must have a double arrow to indicate forward and reverse reactions. Acetic acid turns out to be a weak acid in this reaction that's being shown here. Basically, all that means that it's given up a proton to the water, and those are now the products. So if we are to write the equilibrium expression, we have products. So this is called an acetate ion right here. This is the acetate ion. This is a hydronium ion, so those are the products. They have coefficients of 1, so we don't have to worry about any exponents here. And the reactants are, so those are the products right here on top. And we divide by the reactants. And in this case, acetic acid is a reactant, but water, if you look at the way the equation's written, water is a liquid. And so that becomes a 1. Over here you see that. That becomes a 1 in the equilibrium constant expression. So finally, the equilibrium constant expression for the reaction above is this. Products over reactants, water disappears because it's a pure liquid and has a value of 1, so it drops out of the equation. Okay, so that's our first attempt at writing an equilibrium constant expression. Okay, and like I mentioned before, the equilibrium constant does not have units. Okay, so we're going to practice writing the equilibrium constant expressions for some of these equations. So we'll do so by writing K is equal to the products, which in this case is ammonia, to the power. It's got a coefficient of 2, so that becomes the exponent. So products over reactants. One of the reactants is nitrogen gas. And these would be represented in terms of molarity or the appropriate units for pressure. So we have N2. We also have hydrogen as a reactant. And there is a coefficient of 3 in front of hydrogen, so 3 will become the exponent. So that is what the equilibrium constant expression looks like for this first reaction, which is called the Haber process. And this is used for making ammonia and subsequently fertilizer. Okay, number 2. We start with K is equal to products. Okay, so we have KCl. We make a note of that it's a solid. Times oxygen. Oxygen's a gas. There is a coefficient of 3, so there would be a 2 here also. Over potassium chlorate, which has a 2, but what we're going to do is we notice that potassium chlorate and KCl are both solids, so they are really look like this in the equilibrium constant expression. And so the equilibrium constant expression basically comes down to the concentration of O2 cubed. Okay, another example. This is something called okay, so in this particular case, this one's written incorrectly, so we are going to cross this off. H2O liquid dissociates into H plus OH minus aqueous. Okay, so if we're writing the equilibrium constant expression for that, K is equal to H plus. There's a 1 here, so we don't have to worry about a superscript. Minus, and water is a pure liquid, so that's over 1. So the expression for this would be H plus times OH minus. And then we have another one. We have, let's see. Okay, so in the next example, we actually don't have this here. We have carbon monoxide gas reacting with oxygen gas to produce carbon dioxide. So we have K is equal to the products. The products are a gas, so CO2. There's a 2 here in the balanced equation, and so there's a 2 up on top as a superscript, and we have carbon monoxide on the bottom. There's a 2 in front of that, so that goes there, plus O2. Okay, so all of that, everything's a gas. We have the superscripts in place, and so this is the equilibrium constant expression for reaction 4. Okay, for reaction 5, we have lithium carbonate, solid, dissociating and producing lithium ion and carbonate. There should be 2 minus here. Okay, so K is equal to the products. So we have lithium ion, and there's a 2 here, so we need a 2 here. The other product is the carbonate ion, and again that's aqueous, so that counts in the equilibrium constant expression. All over lithium carbonate, which we see is a solid, so this really becomes a 1, and the equilibrium expression for this then becomes Li, let's put the plus in here, plus squared times the carbonate ion. And finally, the last practice equilibrium constant expression we'll write is this. We have hydrogen gas reacting with iodine gas, producing hydrogen iodide gas. So K is equal to, here we go, products, so HI. The coefficient becomes the exponent over H2 times, and make sure these are times, okay, not plus. H2, so I2, and that's also 1, so we're all set with that, and this is the equilibrium constant expression for number 6. So remember, products over reactants, coefficients become the exponents, and these are products, not addition products. Products multiply. Okay, so this is the form that these take. Now, when we're taking a larger view of an equilibrium these are pictures of generic chemical equilibria systems. We can have reactions where the reactants are favored. We can have systems where the products are favored. And we can have systems where there's kind of a balance between the reactant and the product. So there's a mixture, and the concentrations are roughly the same. So we'll take a look at the first type of system. In this case, the blue molecules are the reactant. The red is the product. So obviously, in this case, there is very little product. And we would say that the numerator is small because that's the product. The denominator is large. So if we have a small numerator, a large denominator, we know the value of the equilibrium constant is going to be much, much less than 1. So this is an important thing to remember. So K is less than 1 basically means the reaction favors the reactants. In a case where the denominator is small and the numerator is large, in other words, most reactant gets turned into product, as is the case in the second picture, we'd have a very large number on top, a small number on the bottom, which means K will be much, much greater than 1, and that means that the products are favored. And then we have a kind of system where the reactant or the system doesn't favor one greatly over the other. The concentrations of the reactants are about the same. And in that case, we have a situation where reactants and product concentrations are about the same and our K is equal to 1. So you do need to recognize these different values, or these sort of qualitative values for K. Now, when we're talking about a chemical system at equilibrium, we're suggesting that it's kind of balanced. So if we have something like this, a balance, and we have, in the lab, sometimes we'd look at one of the old-fashioned pan balances. And if we have an equal amount of material substance here as we do here, it's in equilibrium. And so things are balanced or in equilibrium. But if all of a sudden I add more mass to this side, we know the balance is going to go down. And we also know that the only way to restore the balance might be to take some of this and put over here. So if we took half of it, put over on this other side again, we could reestablish the equilibrium. So a Frenchman named Le Chatelier described this, or developed these ideas to describe what happens to a chemical system which is at equilibrium and then is stressed. How does it go about relieving or reducing the stress to the system? That's what Le Chatelier's principle is about. It's a qualitative treatment, but it's definitely something you should be aware of and understand. Okay, so one of the first examples that we'll see using Le Chatelier's principle is for the Haber process. We've mentioned this before. The Haber process is nitrogen. So we have nitrogen gas, and we have hydrogen gas. They are in equilibria in producing ammonia. Okay, so if the system's in equilibria, and if we look at our chart off to the right here, the fact that these concentrations are stable and unchanging means that at this point, and this point, and this point, the system is at equilibria. So when we have these concentrations are flat. Now notice they are not equal by any means, but the concentrations are unchanging, and therefore the system is at equilibria. All right, so we have a system at equilibria. We have present, and you can imagine that this is what's happening in a steel tank in the manufacturing plant. And then what happens is that at certain time t, some ammonia is injected into the system. So we see instantaneously that the concentration of the ammonia jumps up. Well, now the system has to re-establish equilibria. So ammonia is a product. And if we want to reestablish the equilibria, we see that the product is going to have to shift to the left and thereby produce reactants. So we have to use up what's added and restore equilibria. So the equilibrium shifts left. We say that the reaction shifts left, and that's to offset the stress to the point. And here's the process by which, this is the area by which the system is reestablishing equilibria, and now you see that it has leveled off again, and we have reestablished equilibria, and the concentrations are once again staying the same. Now, because we've added more ammonia, there's a new equilibrium established, the concentrations and new concentrations at equilibrium are going to be different than they were prior to the injection of the ammonia. So this is our new, these are our new equilibrium concentrations. So to put this in words, if we add reactants to the system shifts to the right in order to use up the reactant. So in other words, if we add H2 or N2 into the system, we are going to have a shift to the right that uses up these new concentrations of hydrogen and nitrogen gas to produce ammonia. If we were to add the products, so if we were going to add product, which would be the ammonia, which is the case we already looked at, the system has to shift to the left in order to reduce the amount of product and reduce the stress. So it shifts to the left and it makes more hydrogen and nitrogen gas in the process. If we are talking about a gas phase reaction, which we are in the case of the Haber process, increasing the pressure makes the system shift to the side with the fewest gaseous moles of substance. So if we're increasing pressure, in order to reduce the pressure, we need to look at which side of the arrows has fewer moles of gas. If we're increasing the pressure, then the system is going to move in the direction that has fewer moles of gas, and that will then reduce the pressure. If we did the opposite, if we lowered the pressure, then the system would shift to the side that has more moles of gas, and that therefore it would restore the pressure. So that's a very particular case to gaseous systems. Now, temperature, we said, has a big effect on the equilibrium constant. And so the way we're going to look at this is that if we have an exothermic reaction, we're going to use the heat. Here's an exothermic reaction. We're going to view this as something called heat. And if it's exothermic, then it goes on to the product side because it's being released. So heat is released, and we view it as a product. So if we increase the temperature, by increasing the temperature, it's like adding heat to the system. If we add heat to this system, the way to use, we have a system shift to the left because that will use up the heat. And once it uses up the heat, the temperature will go back down. That's how the system relieves the stress of additional heat. Alternatively, for a reaction which is endothermic, that means the heat is going into the system, it's absorbed by the system. We will write the word heat on the reactant side. And if the temperature is increased, so if we increase the temperature, that's like adding heat, the system is going to shift to the right because that will use up the heat, and then the temperature will go back down. So endo and exothermic are pretty different. In the case of this endothermic reaction, if we were to decrease the temperature, that would be like removing heat. So if we were to remove heat from the system, that means we were pulling it out, then the system would shift to the left to make up for that. So if we decrease the temperature, that's removing heat, and the system shifts to the left to make up for it. Okay, so we have some examples here. We'll walk through these. The problems are actually solved already, but let's take a look. So the first question says, how does an increase in temperature affect the equilibrium concentrations of the underlying substances and K for the following reactions? So we're increasing the temperature. In other words, we're adding heat. In the first exam, question A, calcium oxide plus water produces calcium hydroxide, and the delta H is given as minus 82 kilojoules, which means it's exothermic. And if it's exothermic, we're going to write it as a product. If we add heat to this system, which is exothermic, that's like adding product, and the reaction is going to shift to the left. And they ask us about what's happening to the concentration of calcium hydroxide as the system reestablishes equilibrium. Well, the system's going to shift to the left. That means calcium hydroxide concentration is going to decrease. Okay, so in the first case, they've written heat as a product. An increase in temperature will shift direction to the left, thereby decreasing calcium hydroxide. Okay, in part B, calcium carbonate solid is decomposed into calcium oxide and carbon dioxide. If you look at delta H, it turns out that this is an endothermic reaction because delta H is positive. So we really need to write, for an endothermic reaction, we really should have heat on this side of the equation. And if we are increasing the temperature, we are adding heat. So if I add heat to this reaction, the reaction is going to shift to the right. And they're asking what happens to the carbon dioxide concentration. Well, it's going to be increasing since the product is being produced. So the system shifts to the right here. So it shifts to the right, and we see the increase in carbon dioxide. Oh, and we'll go back after it. They did ask us what is happening to the value of K. We'll look at that at the end. Finally, we have another equation in C. This is also an endothermic because delta H is positive. So we would write heat over here. We add heat, the reaction shifts to the right. They asked us about what's happening to SO2. It's going to decrease. So shift right, decrease in SO2. Now in terms of the values for K, all we have to do is keep in mind that K is equal to the products over the reactants. And in the case of A, we have a situation where the reaction is shifting to the left. And if it's shifting to the left, then the numerator's decreasing, the denominator's increasing, and then therefore K will decrease. In the case of B, the reaction is shifting to the right, which means the products are increasing, and therefore the numerator's increasing, the denominator's decreasing, so we see an increase in K. And finally, the last one is essentially the same thing. The reaction is shifting to the right, and we have products will be increasing, reactants will be decreasing, so overall K will be increasing. Okay, so that's basically how that works in terms of the effective temperature and on an equilibrium constant, and shows you how the differences are between exo and endothermic. Now this chart is an excellent chart. Just basically summarizes all the different kinds of stresses that could be put on a system in equilibrium. Again, we'll just take a look. We know that concentration is going to be a big factor. And what we're going to practice a lot of these shortly. Concentration is a big factor. Pressure, which is essentially concentration for gases. We just saw that temperature plays an important role. We see you can add a catalyst. And there's one here where they talk about the addition sometimes of an inert gas. And this would be in a gaseous system. There's some examples that we'll look on that, but generally an inert gas, if it's not involved in the equilibrium expression at all, will have no effect. So this is kind of a tricky one sometimes that shows up on the College Board or the AP. So the addition of an inert gas to a gaseous system, if it's not involved in the equilibrium, has no effect. Okay, so this is a very good chart to go back and reference, especially as we go through and do a lot of these practice problems that are coming up. Okay, so this is something called the reaction quotient. I think we're going to skip a few of these, practice Le Chatelier's principle, and then come back to this. Okay, so we're going to take a more quantitative look at the equilibrium constant, or this idea of a system at equilibria. We have a new term that we call the reaction quotient. It's written as a Q. Q is a sort of freeze frame, okay? It's a snapshot in time of what's happening to the system. You take a whole bunch of reactants, throw them in there together into a tank, and wait for the equilibrium to occur. And when you first initially put them together and determine the concentrations or the relationships, it's called Q. It's what happens before you've had enough time to reach equilibrium. So as a definition, at any time t, the system can be sampled to determine the amounts of reactant and product present, and this is before it has reached equilibrium. A ratio of products to reactants calculated in the same manner as K. So all the rules that apply to writing K now apply to writing Q, the reaction quotient. And when the system actually does reach equilibrium, then we say that Q is now equal to K, and the system's at equilibrium. What we'll be doing, though, is looking at whether, depending on whether Q is equal to K, in which case we have equilibrium. If we have Q greater than K or Q less than K, then the system has to move in a direction that brings the system to equilibrium. So we'll be either going in the reverse or forward direction to get to the point of equilibrium, and that's determined by Q, which is where you're starting at. Again, we use molar concentration, same as before. We use our brackets. Remember, molar is moles per liter. And again, if we have a general reaction here, A plus B goes to C plus D. This is the equation for the reaction quotient. Okay, so it's going to be a predictor as to whether the forward or the reverse reaction will be favored as the system moves towards equilibrium. Okay, so we have a few problems here. Writing the reaction quotient from the balanced equation. So remember, we need a balanced equation. We have in problem A, the decomposition of dinitrogen pentoxide. This is the equation. It looks to be balanced. Let's see, does it look to 2 and 2? Maybe it's not. I think it's not actually. We have to balance this equation. So we need to balance this. And so if we're going to balance that equation, we go on down below. They have balanced it for us. There's not a lot of room here. So we put a 2 in front of the dinitrogen pentoxide, a 4 in front of the nitrogen dioxide, and now we have a balanced equation. In the part B equation, we have propane and oxygen. We needed to add a 5 in front of the oxygen and a 3 and a 4 in order to balance that combustion reaction. Okay, so we're just practicing writing Q, which follows the rules for writing K. We have products. So nitrogen dioxide is a product, and it has a coefficient of 4, so we have 4 as the exponent, times the concentration of oxygen. Divided by, so remember, products, students always mess this up, so don't be that guy. Products over reactants, we have dinitrogen pentoxide as a reactant. There's a coefficient of 2 in front of it, so we have 2 in the exponent. So now that's our reaction quotient for part A. Moving over to the combustion reaction of propane, where that's all balanced. We have the 5, the 3, and the 4. That balances that equation. Again, products over reactants. Coefficients become exponents. So don't forget your 3 and your 4 and your 5. And then there again, we have the reaction quotient for the combustion of propane. Okay, so that's how we're writing that. There's not a lot of anything new in that case. Okay, so this is a problem now where we're going to actually treat it quantitatively, and we're going to use these molecular scenes or these particulate diagrams and translate those into a data table. And then analyze for the value of Q, compare it to K, and predict which direction the equilibrium should shift in order to achieve equilibrium. So what we're going to have to do is we'll go on the next slide and we'll write out this whole. Okay, so we are looking at A produces B. A is red. B is blue. Okay, so B is the blue, A is the red, so B are the blue guys, and A are the red guys. And we'll go back to, let's make a chart. We're going to make a data chart. So experiment number, let's put it back in black ink. Experiment number will be here. And we have experiment 1. We have experiment 2, experiment 3, and experiment 4. We're going to have to analyze the data. We are going to want to compare, so Q in this case is a concentration of B over A. And they also tell us in the problem that the equilibrium concentrations were found to be this. So the equilibrium concentrations will allow us to calculate K, the equilibrium constant. So at equilibrium, they said that B was 1 point, concentration of B is 1.2 times 10 to the minus 4. Let's see, how do we erase part of this? Okay, so this is the concentration of B at equilibrium. And the concentration of A at equilibrium was given as 2.8 times 10 to the minus 4. So we can actually calculate a value of K before we even start. And we know that that is equilibrium constant is products over minus products over reactants, which will be like this. And K comes out to be 0.43. So the problem is asking us to translate the pictures into data. From the data, calculate our Q. So we're going to calculate our Q. And then by comparing Q and K, we will describe which direction the reaction needs to shift in order to achieve equilibrium. Okay, so let's count the dots. In experiment 1, we have 2 red and 8 blue. So at this point, the reactants are favored over the products. I mean, this is maybe the beginning. And so in the second experiment, we have 7 red and 3 blue. In experiment 3, we have 6 red and 4 blue. Experiment 4, we have 8 red and 2 blue. Now we're going to calculate the value of Q. So Q is simply the number of B divided by the number of A. So 8 over 2 gives us a value of Q equal to 4. 3 over 7 gives us, so 3 divided by 7 gives us 0.43. The next experiment gives us 4 over 6, which gives us 0.67. And the last experiment gives us 2/8, which is 0.25. So these are all the values for Q. And now we must compare Q with K. And there is a little picture I would like to show you. I'm going to try it up here. This is a way to help you remember. If Q is less than K, then the reaction moves in the forward direction. If Q is equal to K, you're at equilibrium. And if Q is greater than K, then the reverse reaction will have to take place so that you go back towards equilibrium. Okay, so let's compare the value of 4, that's our Q for experiment 1, to K. In this case, Q is greater than K, so the reaction must shift to the left. So it's going to shift left in order to achieve equilibrium. In the case of number 2, we have a value of Q equal to 0.43. Well, it turns out that 0.43 is equal to the equilibrium constant. That puts us right down here at the bottom of the curve. So this means there's no shift and that the system is at equilibrium. No shift. Now we look at 0.67. 0.67 is actually larger than K, not by as much as before, so we're somewhere over here. The reaction is still going to shift to the left. And finally, 0.25 is actually less than 0.43, so we're over here on the curve, and the reaction is going to shift to the right in order to achieve equilibrium. So that's basically, if you keep that little chart in mind, it's a good reminder of which direction a system will shift in order to achieve equilibrium based on the relative values of Q and K. Okay, on this slide then, we are given the solution to the problem that we just figured out. So if you take a look, here's our our KC, determined from the data they gave us at equilibrium. And then these are all the values for Q for the various runs of the experiment. And then these are the adjustments that need to be made in order for the equilibrium to achieve, for the system, the chemical system, to achieve equilibrium. This is just another picture that's showing the same thing. So this is the Q is less than K, Q equals K, Q is greater than K, and that's kind of why if you draw this picture that I had before, Q is less than K, and you hit the bottom, that's equilibrium. Q is greater than K up here, then the reverse has to be true. And so basically those are two different graphical ways of describing the same thing. Okay. The next thing is to use the equilibrium concentrations to generate K. This is a whole new quantitative aspect of these kinds of problems. So again, we're doing some more quantitative work. So we're doing quantitative. So we're going to be working with more numbers. Okay, so in some cases we're going to know the equilibrium concentrations. There may be one that we don't know, and we will have to figure out the concentration. So we'll write the equilibrium expression. We'll know the value for the equilibrium constant. Okay. And we'll be able to solve for x. So there's a number of variations on this. You can't just memorize one way of doing it. So you need to understand. Okay. So up a little out of. So this is one of those types of problems where you are given a number of knowns and asked to find one unknown. So in this particular case, we have carbon monoxide reacting with hydrogen gas to produce methane and water. Again, double arrows saying it's reversible reaction, so be looking for those. That's a little bit of a clue that we have a system in equilibrium. They tell us that this equilibrium constant has been measured to be 3.933. Remember, equilibrium constants have no units, so don't worry about units. And then this problem, they give us these equilibrium concentrations. So these are all equilibrium concentrations. And they're asking us to find the equilibrium concentration of methane given the values of all the other equilibrium concentrations that are present. So we write the equilibrium constant expression. First, we want to check and make sure that we have a balanced equation. And if you take a look at that, it appears to be balanced, so that's good. We want to write the equilibrium constant expression. So again, products. So we have our products, which is methane and water divided by the reactants, so over the reactants. Careful here, hydrogen has got a stoichiometric coefficient of 3 in front of it, therefore has an exponent of 3 on the bottom. So we have the equilibrium constant expression. We know the value for K. We know the value for these other two reactants and one of the products. We're asked to find the concentration of methane. So we're solving methane will be our x. We're going to solve for x. We substitute all the values in that we're given. We're given the equilibrium constant, and we're given the values for carbon monoxide, hydrogen, and water. We simply solve for the math, and our answer then is 27.7 molar. Okay, so this is one of the easiest kinds of problems. I mean, basically, you're given everything but one unknown, and you're asked to solve the unknown. So this is by far one of the easiest kinds of calculations, equilibrium calculations to do. The thing you have to be careful about is make sure you know how to rate the expression, products over reactants, and making sure that your stoichiometric coefficients become the exponents. So this is a pretty easy problem in this chapter. Okay, so this problem has quite a few moving parts. It involves calculating the equilibrium constant Kc from concentration data. You are given, so we have to read these very carefully. In order to study hydrogen halide decomposition, a researcher fills an evacuated 2-liter flask with 0.200 moles of hydrogen iodide gas and allows the reaction to proceed. So we have the reaction where 2 hydrogen iodide is in equilibrium with H2 plus I2. at equilibrium, they're telling us something important here. The concentration of HI at equilibrium is equal to 0.078 molar. And we need to find the equilibrium constant Kc. So this is going to involve something new, something that takes a little while to get used to. And it's something called an ice chart. And you'll see why we call it ice chart on the next page. One of the first things to remember in this case is that equilibrium constant expressions always require things to be in molarity. And that's moles per liter. So initially, the flask is filled with 0.200 moles. So this is initially. This tank is, or flask is filled with 0.200 moles. The flask has a 2.00 liter volume. So the concentration of HI in the beginning, okay, so initially is 0.100 molar. So we start off, we put 0.200 molar into this tank, and we wait for an equilibrium to be established. And then we are told that the concentration of HI at equilibrium, so this is a very important piece of information, excuse me, is 0.078 molar. Okay, so we're going to go on to the next slide. And let's see, I think we should put down that the concentration of HI at equilibrium equals 0.078 molar. That's important. Okay, so this is where this is going to take some time to get used to this. The best way to write this kind of problem out is to write the equation. I would always start with writing the equation. And this is kind of an accounting system. I would call this an accounting system for chemicals. Okay, in much the way accountants keep track of dollars with credits and debits and such, this is a way we're going to keep track of what's happening to our products and reactants. So you want to write the equation over here. You don't need to write this column here, concentration. It's sort of understood. But the way this works is we write down our initial concentration, how much we change, and the change is going to be some amount X, doesn't matter how much, and what are the concentrations when we finally achieve equilibrium. Okay, so that's why we call ICE, initial change equilibrium, ICE. These are called ICE charts. Okay, so these are called ICE charts. All right, so initially, when we throw everything into the tank, everything into the tank, we have only HI. And the HI we calculated in terms of molarity, because they gave us moles per liter, we calculated that the concentration initially at the beginning was 0.100 molar. So at the very beginning, before anything happens, I have 0.100 molar HI. I have 0 H2 and 0 I2. Now the system begins to change. It begins to head towards equilibrium. And it's going to change by some amount X. So you have to be very careful when you say how much of it changes. It changes by some amount X. But in this case, I have 2X. So it changes by an amount minus 2X. And if X is changed, then X amount of H2 is produced. And there's a 1 there, so you only have a 1 here. And amount X of iodine is produced. Okay, so that's the change part. 2X of HI goes away. X of H2 and 8X of I2 is produced. Now, what does that mean about equilibrium? Well, I had started with 0.100 minus 00, and I've lost 2X. So the equilibrium concentration is now going to be equal to this expression. The amount of H2 I have is X. The amount of I2 I have at equilibrium is X. Now, the rest of this is basically just solving for the math. But they did give us, this is the harder part, but they gave us an important piece of information. So they said that at equilibrium, the concentration of HI was 0.78. So they are telling me that at equilibrium, the concentration is 0.78, so 0.078, which is up here, which was given, is equal to 0.100 minus 2x, which is right here. So this expression is going to be equal to 0.078, which was the final equilibrium concentration for HI. Now I just have to solve for X. X comes out to be 0.011. And now I can calculate the values that go into the equilibrium constant expression, or that of Q, probably Q or K. We're talking about at equilibrium, so it's really can be K. And so we're going to take 0.011 is X. That therefore equals the concentration of X is this. So this is also 0.011, 0.011. We can calculate this up here. So we can take the value of, well, we actually don't have to, right? We know what this is. This is 0. This concentration was 0.078. And now we plug them all into the expression. So here's your X, the concentration of HI. They're all equilibrium, so we can actually call this Kc. And the value for Kc comes out to be 0.020. And that's equal to Kc. So this is, again, this takes some time to get used to. If you do this in AP or in college, you'll see this quite a bit. But this is one of the hardest kinds of problems that you might see. So once you get used to it, you figure out the ICE charts, you're all good. Okay, so this is another problem. This is a problem where you're determining one of the equilibrium concentrations from the equilibrium constant. So in a study concerning the conversion of methane to other fuels, chemical engineer mixes gaseous methane and water in a 0.32 liter flask at 1200 K. At equilibrium, the flask contains 0.26 moles of CO, carbon monoxide, 0.091 moles of hydrogen, and 0.041 moles of CH4 or methane. What is the concentration of water at equilibrium? The value for the equilibrium constant is equal to 0.26 for the equation given below, which is simply the reaction of methane with water to produce carbon monoxide plus hydrogen gas. First of all, double check and make sure you have a balanced equation. Let's see, one carbon, one oxygen, 6 hydrogens, and we do have a balanced equation, so make a note of that. Okay, so we need to figure out one of the equilibrium concentrations for water. So go about writing the equilibrium constant expression. And in the problem, they're showing it as QC. We are looking at equilibrium values, so it's also KC. And if we look at this carefully, we have products over reactants, so we have CO. We have a 3 here as a coefficient for hydrogen, so we need the 3 as the exponent. We divide by the reactants. Methane and water are there as with coefficients of 1, so we have methane and water. So this is our equilibrium constant expression, and they actually give us a value of the equilibrium constant, so that's equal to 0.26. So one of the catches here, one of the things that could mess you up is the fact that they give you the moles of each of those and they tell you the volume of the flask. So one of the first things you need to do is convert the concentrations or determine the concentrations based on moles per liter. So we have a 0.32 liter flask. First we're given 0.26 moles of CO, so 0.26 moles per 0.32 liters gives me 0.81 molar for carbon monoxide. Likewise, I have 0.091 moles and 0.32 liters for hydrogen. And finally, I have 0.041 moles and 0.032 liters or 0.13 molar for the methane. And I am given the equilibrium constant as well. So this really comes down to solving for this. This water is our X. And so over here, they have done that. They have solved for water. It's a matter of substituting into the expression for the equilibrium constant. It's equal to, here's our 0.26 right here, which was given. You solve this, be careful when you're doing the math of the cubes and the squares and all those exponents. And the value for the equilibrium concentration of water comes out to be 0.53 molar. So check for balanced equation, write your expression, products over reactants, coefficients become exponents, be sure you're substituting in molarities, concentrations, and then you simply solve for the missing variable or reactant, which in this case was water. Okay, so this is another variation on an equilibrium problem. Okay, this is another type of equilibrium problem. we are going to be determining equilibrium concentrations given the value of the equilibrium constant and the initial concentrations that we have at the beginning of the process. So fuel engineers use the extent of the change of CO and H2O to CO2 and H2 to regulate the proportions of synthetic fuel mixtures. If 0.250 moles of CO and 0.250 moles of water are placed in a 125 milliliter flask at 900 K, what is the composition of the equilibrium mixture? At this temperature, Kc is 1.56 for the equation below. So we have carbon monoxide plus water producing carbon dioxide plus hydrogen. And key thing here, they give us the equilibrium constant, and they are talking to us about, they're giving us the molarity. So in other words, they're giving us the initial concentrations that are going into the big tank. So initially we have, and so this is where you have moles, and you have, this isn't a big tank, it turns out it's a 125 milliliter flask. So make sure you convert that to liters, so 0.125 liters. And we start with 0.250 moles of carbon monoxide. So you need to get that converted into concentration. So 0.250 divided by 0.125 is right here. And I believe that comes out to be equal to 2 molar. So this isn't a tank, it's a flask. All right, and likewise we have the same concentration of water as well. We have 0.250 moles. It's going into the same 125 ml flask, so we also have 2.00 molar for both of them. So initially that's what we have. In the beginning we have no product, so it's 0. We have no CO2, we have no H2, so those are 0 in the beginning. So as this system begins to reach towards equilibrium, it changes by minus x, and that's a 1, so this is a minus 1x or minus x. Likewise, this is a minus 1 H2O, so this is minus x. As this is decreasing, as these reactants are converting to products, the products grow in at plus 1x, because this is also 1, plus 1x. And what they tell us then is, so at equilibrium then we have 0.200 minus x for carbon monoxide, 0.200 minus x for water. We have x for CO2 and x for H2. So those are the equilibrium concentrations that we have at this point, and they gave us a value for Kc. So the next step is going to be to write the equilibrium constant expression. So we have Kc, we have products over reactants, all the coefficients were 1. We take what we have at equilibrium from our ice chart. Remember that was called an ice chart. So we have an ice chart, and we take the values at equilibrium, which for carbon monoxide is x, for H2 was x. The reactants are 0.200 minus x, each of them. If you put that together, you come out with this algebraic expression right here, x squared over 0.200 minus x squared. And that is equal to the equilibrium constant, which I believe was 1.56. We could check back on that. So if we have, now it's algebra, so we have, if we take the square root of both, that's what they've done here. They've taken the square root of this, and they've taken the square root of that. Obviously, a concentration isn't going to be a negative number, so we don't worry about that. We have X now is equal to 1.11 molar. And so that actually gives us the values for CO2 and H2. And we know that the reactants were 0.200 minus X, or 0.89. And there's 0.89 molar. So these are the equilibrium concentrations for that system that was described on the previous slide. So we started with a certain set of conditions. Some initial amounts were given a Kc at equilibrium, and from that we can find the equilibrium concentrations for all of the reactants and the products. And again, this uses an ice chart, which, as I said, is just an accounting system for a chemical reaction. Okay, so this was another example. Hope that it's becoming clearer at this point. Okay, so this is another kind of equilibrium problem. Again, what you'll see if you do enough of these is that they all do look very similar in the end, but you do have to understand what you're doing. The research and development unit of a chemical company is studying the reaction of methane, CH4, and hydrogen disulfide, sulfur dihydride, and which is H2S, two components of natural gas. And so we have an equation where we have CH4 plus 2H2S goes to CS2 plus 4H2. I want to check and make sure first that it's a balanced equation. It looks to be a balanced equation. Yes, it is. So we'll make a check on that. In one experiment, 1 mole of methane, CH4, 1 mole of CS2, carbon disulfide, 2 moles of dihydrogen sulfide, and 2 moles of hydrogen gas are mixed in a 2 milliliter vessel at 960 degrees C. At this temperature, Kc is 0.036. So that's a very important piece of information. Everything is the reactants are each, nope. Let's just go through this. We have 1 mole of methane, and it's in a 250 milliliter vessel, so it's let's convert to liters, 0.250 liters. We have 1 mole of carbon disulfide. We have 2 moles of H2S and 2 moles of H2. And they're all put in together into this 2.250 liter flask. So at first the question in part A says, in which direction will the reaction proceed to reach equilibrium? So when you see a question like that, you're basically going to need to calculate Q. So you have to calculate Q and then compare it to K. So in order to calculate Q, we're going to have to write the expression. We're going to have to turn all of those quantities of moles into molarity. And then we can substitute in, find Q, and then compare it to the given value of K, which was 0.036. And then part B asks if methane, the concentration of methane at equilibrium is 5.56 molar. What are the equilibrium concentrations of the other substances? So we'll go to the next slide to get this all set up. First thing we have to do is to calculate the molarity of all of the products and reactants. So that's very important. Everything's in the same flask. So it was 250 milliliters. We need to turn that into liters because we're talking molarity. So remember, molarity is moles, which we're given, per liter. So we've done that. We have the concentrations of the reactants and the products, and that's a good start. Okay, so now we're going to transfer the equation over to this slide. Actually, I think these are concentrations. These were initial concentrations, I believe. Okay. On the next slide, we're going to write out the reaction, and then we're going to find our value for Q. And we will go ahead and continue with the problem. Okay, so what we're going to do is write the equation. It was CH4, so CH4 plus 2H2S goes to carbon disulfide plus 4 moles of hydrogen gas. Okay, so, and we were also told, I'm going to write it down here, that K was equal to 0.036. So the first thing we have to do is to write an expression for Q. So Q, products over reactants, so is the concentration of CS2. This is a 4, so we're going to have hydrogen to the 4th. This is a 4 over CH4 and H2S. There's a coefficient of 2, so this must be 2. Now we have to substitute all these numbers in that we calculated on the previous slide. So, okay, so we're going back from the previous slide. And the initial concentration, so we throw all of this into the 250 milliliter flask. This is what we're starting with, which is why we're looking at Q. We have carbon disulfide is 4 molar. H2 was 8. So 8 to the 4th. Divided by methane. Methane was 4. And sulfur dihydride was 8.0 to the 2. Okay, so we have to do all the math on this to find out what Q equals. Okay, so we get all the math done on this, and it comes out to be 64.00. So we have Q, we have K. Q is 64. K is 0.036. So Q is much greater than K. So if we go back to our chart, Q is less than K, Q is equal to K, Q is greater than K, then what we see is the reaction is going to have to shift to the left. So the reaction will shift left. In other words, the reverse reaction will be favored because we have too many products right now. Okay. Okay, so now what we're going to do is the second part of the question gives us the equilibrium value for the methane at 5.56 molar. We know the equilibrium constant. The equilibrium constant was 0.036. We know all of our initial concentrations, and so what they're asking us to find is the equilibrium concentrations. So we throw everything in, we have initial concentrations. The system, as we just figured out, proceeds to the left, so reactants become products. Eventually everything balances out. We achieve equilibrium, and then these reactants and products have an equilibrium concentration. And that's what we need to figure out. So we're going to use an ice chart. The thing to do is to start off by writing the equation, which I've already done. So we have methane plus 2 dihydrogen sulfides produces carbon disulfide plus 4 hydrogens. Okay, so we're going to start with ICE. Initial. So let's figure out the initial concentrations here. Initially we had 4 molar of methane. We had 8 molar of dihydrogen sulfide. We had 4 molar of carbon disulfide, and we had 8 molar of hydrogen gas. Those are my initial concentrations. They were given to us at the beginning. And so we're going to do the change. So minus X. This will be minus, there's a 2 in front of this, so minus 2X produces X, so plus X, and then this is a 4, so plus 4X. So the equilibrium concentrations we have then are going to be 4 minus X, 8 minus 2X, 4 plus X, and 8.00 plus 4X. Okay, so here we are. These reactants are going away, so these are minus signs, and the products are growing in, so these are plus signs. Now we have expressions for the equilibrium concentrations of all of the chemical species in this flask, and they give us one very useful piece of information, and that is that the equilibrium concentration of methane is 5.56. In other words, 4.00 minus X equals 5.56. And this is going to be the key for us to figure out everything else. So we're going to solve for X. And so once we solve for X is equal to 1.56. And now we can go ahead and figure out all of these values for the rest of them. So for H2S, this is going to be 8.00 minus 2 times 1.56. This will be 4 For CS2, 4.00 minus 1.56. And for H2, it'll be 8.00 minus 4 times, no, plus, I'm sorry, these are plus 1.56. And if we go to the next slide, you're going to see this all worked out for us, and you'll see the final answer. Okay, so they've done the same thing that we did. And what you can see is that we have a value, our X, right here. And then we have our final concentrations for all the reactants. We knew methane was this at equilibrium. We have 11.12 for H2S, 2.44 molar for CS2, 1.76 molar for hydrogen gas. And so these are all the equilibrium concentrations, and this problem started with initial concentrations. We were given an equilibrium constant value that helped us a lot. And then finally, we were given a key piece of information that the equilibrium concentration for methane was 5.56. That allowed us to write an expression and solve for X. And then that allowed us to do all the rest of the calculations. So this is a pretty complex problem. I think that if you can understand this, then you're in great shape. And if you don't right now, don't worry about it too much. But this is definitely one of the classic equilibrium concentration kinds of problems. All right, well, that's it for these kinds of problems. This slide is basically summarizing all the steps in these kinds of problems. As you can see, you're going to write the balanced equation. You must start with the balanced equation. You might want to write the reaction quotient expression, so you might write Q. All the amounts need to be in molarity. You may need to do an ice chart. It's a possibility to do an ice chart. And then simply you're going to do the math for X. And then basically there's a little bit of information here that we're not going to worry about. We're not going to worry about it for advanced chem. This is something you do later for AP or college chem. Actually, college will use a quadratic equation. So this is later. You found your X, and then you write out your equilibrium values. So, and there's a lot of variation on this. As you just saw, there's quite a few different kinds of problems, so you really do need to, you can't memorize, you need to understand. And this is just the beginning, so. Okay, so they're actually more at the end of this unit. So we're skipping to this, which would normally be a separate worksheet. So this is these next 4 slides are important practice. And what we have again is the Haber process. Right here, N2 plus 3H2 goes to ammonia. They're showing that it's exothermic. And what happens in this particular chart is that they're showing you which one they're changing. So in this case, we're adding nitrogen. So this is the variable we're changing right here. And then we're asked what is happening to H2 and H3 and what happens to the equilibrium constant. Okay, so if we add a reactant, then the system will shift to use up the reactant. In other words, the system is going to shift to the right. It's going to shift to the right, shift towards products. Adding hydrogen. So this is a variable we're changing. We are adding hydrogen. So in order to reduce the stress, the equilibrium is going to shift to the right. And in terms of N2, what's going to happen is that this is going to decrease because it's also being used up as it makes product. And NH3 will increase because more product is being made. The equilibrium constant stays the same. So keep in mind, the only thing that changes the equilibrium constant is the temperature. Okay. So now we're adding ammonia. Ammonia turns out to be the product. If we add the product, the system is going to need to shift to the left in order to reduce the stress. If the system shifts to the left, then the amount of ammonia will be increasing. Some of that's going to be produced. Hydrogen gas will also increase because that's going to be produced. And ammonia was the variable we're changing. And again, the equilibrium constant will be the same. Now, imagine what happens if you actually remove some of the reactant from the system. How does the system respond to make that up? Well, it's going to shift to the left. To produce more nitrogen. So this was the factor we changed. So it's shifting to the left. And therefore, at the same time, if it's shifting to the left, some more hydrogen will be increased. Okay. If we pull this out, the reaction shifts to the left. So we're going to increase the amount of hydrogen, but now we're going to decrease the amount of ammonia. It's going to be turned into reactant. And again, the equilibrium constant stays the same. Lastly, if we remove hydrogen, so if we remove hydrogen, that's basically like removing nitrogen. It's removing a reactant. So the equilibrium is again going to shift to the left. If it shifts to the left, then the nitrogen will be produced. This was the variable we changed. Ammonia is going to decrease because that's going to be consumed, and the equilibrium constant will stay the same. Okay, in the second half of this chart, let's just put up here the reaction again. So N2 plus 3H2 produces 2 ammonias. If I remove the ammonia, so this time if I remove, and this is plus energy, plus whatever it was, heat. If I remove NH3, the equilibrium is going to shift to the right to compensate. And so this actually, the system will shift to the right. Okay, so if we remove the ammonia, the equilibrium is going to shift to the right. The amount of N2 will decrease. And because it's being used up as the reaction goes forward, H2 is also going to decrease. The ammonia is going away, so that's not an effect. And again, the equilibrium constant will remain the same since the temperature stays the same. Okay, so now we're going to look at a change in temperature, which hopefully will alert us to the fact that the equilibrium constant is probably going to change. All right, so if we increase the temperature, that in this reaction is like and then we wrote heat on the exothermic or product side. So if we increase the temperature, that's like adding heat to the system. If we add heat to this system, it's going to shift to the left to use up the heat. If it shifts to the left, then the concentration of N2 is going to increase. Concentration of H2 will also increase. And the amount of ammonia is actually going to decrease because it's going to be used up. And now we have to ask ourselves, well, how does this affect the equilibrium constant? We know it really is going to affect it. So again, we say the equilibrium constant is products over reactants. So right now, if we're increasing the temperature, we've said that the N2 and the H2 will increase. They happen to be reactants, so they're on the bottom. So the denominator's getting bigger and the numerator's getting smaller. So this means that K is going to decrease. So once again, if we take a look, if the reactants are increasing, they're on the bottom, and the ammonia is going to decrease, that's on top, our overall K is going to decrease. Now let's take a look. If we decrease the temperature, that's like removing heat from the system. If we remove heat from the system, the equilibrium will shift to the right to produce more heat to make up. So the system shifts to the right. That means the concentrations of N2 will decrease, H2 will decrease, ammonia is going to increase, and if the products are increasing and the reactants are decreasing, that means K is getting larger, so K is going to increase. Okay, so that's pretty much it for any change in the equilibrium value constant. Only depends on temperature. Now let's take the case where we're increasing pressure. When we have an increase in pressure, we want to reduce the pressure. In order to reduce the pressure, we need to have the equilibrium shift to the side with the fewer number of moles of gas. Well, if we take a look at it, on the reactant side, we have a total of 4 moles. So we have 1 N2 plus 3 H2 for a total of 4 moles. 4 moles over here. And we have 2 moles over here. So if we've increased the pressure, we need to shift to the side with the fewer number of moles. And that would obviously be towards the product side. So the system is going to shift to the right. That will reduce the amount of gases, the moles of gas, therefore it reduces the pressure. If the system shifts to the right, then we are going to decrease the amount of nitrogen, hydrogen, and we're going to increase the amount of ammonia produced. And basically in this case, the equilibrium constant will stay the same. And in the case of a decrease in pressure, we're going to need to compensate, so the system will shift to the side with more moles of gas, which means it's going to shift to the left. If the system shifts to the left, then the N2 will increase, the H2 will increase, and ammonia will decrease, and the equilibrium constant will stay the same. Okay, so that is a picture of how Le Chatelier's principle works in a qualitative sense. We're not working with numbers, we're looking at a picture of what's happening. So we'll take a look at a couple more of these as well. And after we do this, we'll go back to doing the more quantitative work on equilibria. Okay, so in this new example, we have an endothermic reaction. The energy is on the reactant side, so it's endothermic. Our equilibrium constant expression would look like this. Square, nope, sorry. There's nothing here. And this will be I2. And let's get, oops. This will be I2. Okay, so we're going to take a look at this. And so again, they show the example. If we add hydrogen gas, the equilibrium must shift to the right in order to use up that extra hydrogen gas. In the process, iodine decreases, hydrogen iodide increases, and the equilibrium constant remains the same. If I add, likewise, if I add I2, this is the one that's changing. The equilibrium is also going to shift to the right. So it's going to shift to the right to alleviate the addition of I2. So H2 will be consumed, so H2 is going to decrease as the response is made. At the same time, HI is going to increase because more hydrogen iodide is being produced. And the equilibrium constant will remain the same, as only temperature affects the equilibrium constant. In the next scenario, if I add HI, so if I add HI, which is the product, the equilibrium will shift to the left. If that shifts to the left, then H2 will be produced, I2 will be produced, and the equilibrium constant will again remain the same since we're not changing the temperature. If I remove H2, so now what if I remove some of the reactant? The equilibrium is going to shift to the left to make up for that. In the process, it's going to shift to the left. I2 is going to be increased. I2 will increase, and HI will decrease. And the equilibrium constant will stay the same. Same thing, if I remove I2, this system will shift to the left to make up for it. H2 will be produced. HI will be consumed, and equilibrium constant will be the same. Okay, well now what if I remove some of the product? If I remove the product, the equilibrium is going to shift to the right to make up for that. H2 will be consumed, I2 will be consumed, equilibrium constant will stay the same. And now here's the two situations where we're going to actually have to worry about the equilibrium constant changing value because we're messing around with the temperature. If I increase the temperature, that is like adding heat. If I add heat to this reaction, the equilibrium is going to shift to the equilibrium is going to shift to the right. So if I increase the temperature, the equilibrium is going to shift to the right. If the equilibrium shifts to the right, then H2 will be decreasing, I2 will decrease, HI will increase. And if HI is increasing, that means the denominator is getting bigger, the numerator is getting smaller, so the value of K will be increasing. So take a look. So HI is going to go up, my numerator is getting larger, my denominator is getting smaller, therefore the value of K will be increasing. Now, if I actually decrease the temperature, that's like removing heat. The system will shift left, H2 will go up, I2 will increase, HI will decrease, and now basically I've made my numerator smaller and my denominator bigger, so the value of K will decrease. And if I increase the pressure, in this case, we have 2 moles on each side. So there's 1 mole of gas on each side. So there's 2 moles on each side. So the system has nowhere to shift to. So it's going to stay the same. The same thing if you decrease the pressure. Both sides have 2 moles of gas. So it will also stay the same. So in this case, these will all be the same. Okay, and on this last example, I think that it's worth writing out what the equilibrium expression is, or so that you can see what's actually going to affect things. And they're giving us a hint on that. So K, in this case, will be equal to Na plus, it's aqueous, let's see, maybe we can't do it there. So K is going to be equal to Na plus times OH minus and over 1, because NaOH is a solid, and so that goes into the equilibrium expression as a 1. So if we have our reaction and we add sodium hydroxide, it doesn't show up in the equilibrium constant, so it's not going to have an effect on the equilibrium. So this is none. If we add sodium hydroxide into the system, the concentrations of these would go up because they're going to dissolve. All right. Okay, and looking at number 1 again, if we add the sodium hydroxide into the, imagine we're putting it into a beaker, and some of it dissolves completely. There's just so much sodium hydroxide that'll go into the solution. So we get to the point where we can't add any more, and because sodium hydroxide is a solid, it doesn't show up in the equilibrium expression. This is going to actually stay the same. You're going to get just so much in here and it'll stop. So that's the same. And K will also be the same. So now if I were to add sodium chloride, in other words, if we add sodium, the equilibrium is going to shift to the left, and so we added sodium, The amount of sodium hydroxide is going to increase. The amount of OH minus is going to decrease. And the equilibrium constant will be the same because we're not changing temperature. Now let's say we're adding hydroxide ion. So we're adding hydroxide ion here. Again, the equilibrium will shift to the left. The amount of sodium hydroxide will increase. The amount of sodium will decrease since it's got to react with something. And K will stay the same. Now let's take out H plus. Let's say we're going to add H plus. Well, now this is a little bit different. H plus, if I add H plus into the beaker that has sodium and hydroxide, H plus is actually going to react with OH minus, which is essentially saying the same thing as I'm going to remove OH minus. If I remove this, the equilibrium will shift to the right. The amount of sodium hydroxide would decrease. The amount of sodium will increase because some of the sodium hydroxide will produce more sodium. Equilibrium constant remains the same. Now we have the effective temperature that we're going to take a look at again here. And what we notice is that this is an exothermic reaction. So increasing temperature is like adding heat. If I add heat to this system, it's going to shift it to the left in order to use it. If the system shifts to the left, then it's going to increase the amount of sodium hydroxide, decrease the amount of sodium, decrease the amount of hydroxide. And now take a look at this. What's going to happen to the value of K? The amount of reactant is going to increase. So that means my denominator gets larger. My numerator is getting smaller. So the value of K is going to decrease. Finally, decreasing the temperature is like removing heat. So if I'm removing heat, the reaction is going to shift to the right. The amount of sodium hydroxide will decrease. The amount of sodium will increase. Hydroxide will increase. And in this case, the numerator is going to get bigger, the denominator smaller, so the rate constant will increase. And if we actually take a look at this, and we're going to change the pressure, none of these are gaseous systems. There's no gases in anything here. So there's going to be no shift in the equilibrium because there's no gases here. Same thing as decreasing the pressure. And basically, everything about the system will remain the same. Okay, so that's a lot of practice on Le Chatelier's principle. I think that's good for now. And we'll wrap that up and kind of close out the idea of a qualitative relationship. And we will go back to looking at quantitative relationships for equilibrium constant. Okay, so we're kind of winding down for the year. There's a few things about acids and bases that would be useful to know as part of a chemistry class. And so you have a lot of experience with these things in your daily life. We have vitamin C, which is ascorbic acid. And the ascorbic acid, comes from these protons. You have citric acid. So here's a proton, here's a proton, there's a proton. So citric acid obviously comes from citrus fruit. Vinegar, we have acetic acid. So that's a component of vinegar. You have aspirin, which is called, this is the part of aspirin that makes it an acid. Acid is called acetyl, fancy organic name, acetyl salicylic acid. And so these are all different acids that you come across on a regular basis in life. This one's actually phosphoric. This is a little bit different than the other acids, which are called organic acids. This is called an inorganic acid, and phosphoric acid is present in soda pop. So here are the protons on that guy. Anyway, these are acidic, these are acids, and you do come across them in your daily life on a pretty regular basis. Likewise, so you've learned, you know a little bit about acids. You also come in contact with bases. Strong bases, bases basically contribute hydroxide ions. So baking soda is a weak base. It's NaHCO3. So that's a weak base. And you know, if you take baking soda and vinegar and mix it together, a neutralization happens and you get a lot of fizzing, get a lot of carbon dioxide produced, and it's a classic volcanic chemistry experiment. Another kind of base is ammonia, so that's NH3. We've talked about that. Soap contains lye or potassium hydroxide, so this is potassium hydroxide. Drano is also hydroxide. And Phillips milk of magnesia, this is also actually MgOH2. This is a strong base, much like sodium and potassium hydroxide, but it's, if you've ever had this, it's a milky white solution. Milky white. And that's because magnesium hydroxide doesn't really dissolve well in water. So those are some examples of acids. These are some examples of bases. The characteristics of acids and bases. Acids taste sour. They are corrosive to metals. They'll change litmus paper to red, so that you might have done in biology. Mostly in chemistry, we use pH paper, but more often than not, now we use pH electrode, which measures the pH of the acid directly. They become less acidic when mixed with bases, so you might know that that's a neutralization reaction when an acid and base mix. And they react with metals to produce hydrogen gas. And we've seen this already. We've reacted zinc with HCl, and we've reacted magnesium with HCl, and we've had these reactions where we've had zinc chloride and hydrogen gas. So there's the gas, we need a 2 here. Same with magnesium, and HCl makes magnesium chloride plus H2 gas as well. And we also need a 2 here. So we have looked at those as part of our demos throughout the year. And one of the fun things we usually do in this unit is to experience the sourness of acids with some warheads. So there's several acids contained in a warhead to make them really sour. Okay, bases, they feel slippery. If you get them on your hands, they are very slippery. They change litmus paper to blue. And of course, they become less basic when they're mixed with acids because they also have a neutralization reaction take place. So those are some characteristics. The most important model for acids and bases that people will study today or is the main focus of a lot of chemistry classes. This is this one called a Bronsted-Lowry acid-base theory. It simply says that acid is a proton donor. So anything that can donate a proton, which is H plus, is an acid by this definition, and anything that can accept a proton is considered a base. So if something, an example might be ammonia. Ammonia has a lone pair of electrons, and it can grab a proton, so it can accept a proton, and it becomes NH4 plus. Then we know ammonia is a weak base. So those are the definitions. There are other models, and there are other definitions, but these are the most common that's used. So an acid-base reaction can be viewed from the standpoint of reactants and the products. And what we can do is we can imagine acetic acid. So this is what makes it an acid. Can react with a weak base. And this is a weak base, so these protons will grab it. So proton donor, proton acceptor, and we end up with something that looks like this. So an acidic reactant will produce a basic product, and the two will constitute an acid-base conjugate pair, which simply says, oh, this is a 4, which simply says that this and this are related, and this are related in this model. Okay, not a huge deal. Something to learn later on. All right, and this is actually a picture of it, of what happens on a molecular level. You can actually see the orbitals in this case and what's happening. So in the case we have HCl, which is a strong acid, and so this is your chlorine, and this is your hydrogen, and it's reacting with water. We know from all of our studies that water has a lone pair of two lone pairs of electrons. That lone pair of electron is capable of snagging the proton off of HCl. And what happens, it leaves behind Cl minus, and we have H3O plus. So that's an example of a Bronsted-Lowry acid-base reaction, and we can relate this with this, and water with this. So by the definition of in a Bronsted-Lowry acid is an H plus donor. So here's my donor. And a base is an H plus acceptor. So this is accepting the proton. And then what happens is we have, this is now what we call a conjugate base. Because now this is becoming a proton acceptor. And of course that would be in the other direction. And this is now, this has an extra H plus, so this is now what they call the conjugate acid. Likewise, we have another example where we have the base. This case is ammonia. So again, a base is an H plus acceptor. Water in this case is the H plus donor. These electrons can snag the proton on water. We end up with NH4, and then we end up with OH minus. So here's an OH, and you've got 3 lone pairs of electrons. And in this model, we relate this with this. This is now called the conjugate acid. And this is now called the conjugate base. And I'll put some reading information on this. We're not going to go into a lot of detail. You just need to know some of the differences. So you've heard the term pH over and over again over the years, I'm sure. pH is just a measure of acidity, or it's a measure of the concentration of H+. H plus basically has many names. It's called the hydrogen ion, the hydronium ion, or the proton, or it's written as H plus like this. These are all equivalent descriptions, okay, for H plus. H3O plus, or this hydronium ion, is produced by acidic compounds. And the idea of pH is simply a mathematical description, and it's the negative log of the hydronium ion, hydrogen ion concentration. So remember, this is the molarity. Likewise, you can calculate pOH, which is the same mathematical expression applied to the hydroxide ion, which is basic, makes something basic. And then if you want to relate the two of them together, pH plus pOH is equal to 14. So pH is important in a lot of calculations, and in terms of a daily thing, if you look, our blood is around pH 7.4. We always think of something that's neutral. If we have a neutral solution, we expect that its pH is around 7. So blood is slightly basic. And remember, the lower the pH, the more acidic. So low pH means more acidic. This is something to remember. Means more acidic. High pH means more basic. And again, 7, we think of 7 as what we call neutral. Okay, and so blood's a little bit basic. Milk of magnesia, which we said earlier was a base, is 10.5. Ammonia is 11.9. And detergents are around pH 10. If you go down, vinegars, so vinegar, which is acetic acids, around 2.4. Stomach acids is between 1 and 3. So these are some common household chemicals, and these are their pHs. And what you might not know is usually people think you can actually have pH can be greater than 15, and pH can be negative. And usually people don't think like that because biological systems have pH. When you talk about pH in biology, it's usually between 1 and 14. But pH can be negative and pH can be 15 or more. Okay, anyway, so that's just some ideas about. All right, one of the very last topics will be titrations. And a titration, there are videos on titrations and the actual process. This would have been the last lab for the year. And basically what's done is that you have an unknown acid. So this would be an unknown acid. This would be something called a burette. And you would, this would contain a known amount of base, a base with known concentration. You would add an indicator in here. You would add something called an indicator. which says that when the pH became neutral, in other words, when the number of moles of acid equaled the number of moles of base, the indicator would turn a faint pink. The indicator in this particular case is phenolphthalein. You would drip this in, and you would be stirring this around. And when you had just as many moles of base added to this unknown acid, you would see this slight pink over here, which is called the end point of a titration. That's the end point when the indicator changes color. And then you would know the volume. You would know how much of the base you added. And you would be able to you would know the molarity, you would know the volume, and you could find how many moles of base you added. And then you could figure out the molarity of the acid from doing this kind of experiment. There are some links to videos if you want to watch it, but it's a very, very common thing to do in chemistry lab. When you do some titrations, depending on the acid involved, usually depending on what the acid would be, maybe what the base would be, your end point, which is when you have the color change, would occur at different pHs. And so you would pick your indicator. These are all examples of things called indicators. You would, the most common one, the one we would have used in the lab, is called phenolphthalein. But the color changes occur at different pHs, and for most of them, the one we would have done, it would have gone from clear to pink, bright pink. But you would pick your indicator based on when you thought your color, your endpoint would be reached. So there's a lot of thinking that goes into this. Mostly you could just try it and then pick the right one. So these are what indicators do. When you've neutralized the acid with the base, the color changes, and you would have a pH associated with that. So, and you would pick your indicator based on that. And this one here, called phenolphthalein, is the one that we would have used in our titration. So up close, this would be the beginning of the, we'd have the unknown acid in there before any titration had taken place. This is my indicator, phenolphthalein. This is what it looks like on a molecular level. It's a pretty fancy molecule, and it's colorless. But then when you have reached the endpoint, that next drop of hydroxide right here will change the structure from that to this. And when that changes the molecular structure, the color now becomes pink because you have changes in the bonds. So changes in the molecular structure changes the color. And the changes in the molecular structure depend on the pH. So that's basically what we would have seen. This bright pink would have been what we call overshoot. You would be really targeting for a much fainter pink in order to hit the endpoint where you really needed to. Once you do a calculation, once you complete a titration, there are calculations that you do. The equation that's most often used is this one called MAVA. And basically it says that the moles of the acid, which is the molarity times the volume of the acid, is equal to the moles of the base. So molarity of the base times the volume of the base gives you moles as well. There are a number of sample calculations here. We'll work through each of them, and you'll see the utility in doing a titration. So once again, a titration is done, say if you have you have an acid, its concentration is unknown, you can titrate it with a base, and the base will have its concentration known, and if you know the volume of the base that's used to get to the equivalence point, then you can calculate the molarity of the acid. Okay, so we'll start first by writing this equation, and it starts with moles of acid equal the moles of base. And we'll write it out in terms of an equation. So MA times VA equals MB times VB. MA is molarity, so we know that's actually moles of acid per liter of acid equal moles of the base divided by the liters of the base used. Now we have the volume of the acid, so that would be in liters. What you'll find out is if all the units are the same, then you can use the units of milliliters for the volume. Otherwise, convert it to liters. So that's times the liters of the acid. This is times the liters of the base. So if you look at this, liters would cancel with liters, liters cancel with liters, and you're back to moles of acid equal moles of base. Okay, in the first example, we have 15 milliliters of 0.500 molar sodium hydroxide. So the sodium hydroxide is a strong base. We are titrating 25.0 mils of acetic acid. Acetic acid is a weak acid. And we do not know the concentration, so concentration of acid is the unknown. So we're going to use the equation MAVA equals moles base, moles volume base. So MAVA equals MBVB. We're looking for MA, the concentration of the acid. So we can solve it for, we'll just solve for this. MA equals MBVB divided by the volume of the acid. We can substitute our numbers in here. Molarity of the base was 0.500 molar. The volume of the base used And in this case, we have two volumes are both in milliliters. Those units would cancel, so we don't have to convert to liters. If you're unsure, convert to liters. So this comes out to a 15.0 milliliters divided by the volume of the acid. So the acid had to be measured very carefully. And we have 25.0 milliliters. So if you look at this, these volume units will cancel, and the molarity, or the concentration of the acid, will come out to be 0.300 molar CH3COOH, acetic acid. So that's basically how you do a titration calculation. You use this equation right here, where you relate the moles of acid to the moles of base. And this is true at the equivalence point, which is where your color change will take place. If you're using an indicator, or where your pH jumps way up if you're following the titration with a pH electrode. Okay, we have another practice calculation. So I'm just going to write this up here, titration calculation. And in this particular problem, we are looking at we are looking for the volume of potassium hydroxide, the base, that will neutralize 15.0 milliliters of 0.400 molar H2SO4. Okay, for this problem, we'll start writing down the information. And this one's a little bit different because we have sulfuric acid, which provides 2 protons for every 2 moles of protons for every 1 mole of sulfuric acid that's used. So we're going to put another factor in there when we do the calculation. So we're looking for the number of mils of base that'll be used to neutralize. So the volume of the base, BB, that's used to neutralize 15.0 mLs of, this is volume of the acid, and the concentration of the acid is 0.400 molar, so molarity of the acid. And we are looking for the molarity of the base. The molarity of the base is 0.200 molar. So we, and we'll make a note up here that H2SO4 is diprotic, which means that it releases 2 protons. And in other words, for every 1 mole of H2SO4 we have, we get 2 moles of H+. Okay, so we have all of our information lined up here. We can start with moles of acid, So MAVA equals MBVB. Moles of acid equal moles of base. We are looking for the volume of the base, so we're looking for this. It's our unknown. So we're going to solve for that. And first, I'm going to write it all out first. So MA, the molarity of the acid, is 0.400. And again, moles of H2SO4 times per liter times 15, so 0.015 liters of the H2SO4 equals 0.200 moles per liter of hydroxide ion times X, which is the mole volume of the base. There's the one extra term that we need to put in there so that we end up with the correct number. Because of the fact that sulfuric acid delivers 2 protons for each mole of sulfuric acid, we want to put in another kind of it's a conversion factor, but it's also kind of a molar ratio. So 1 mole of H2SO4 gives me 2 moles of H+. Okay, so now we're going to go ahead and solve for X. So X, or which is also the volume of the base, is equal to 2 times 0.400 times 0.015 divided by 0.200. If you cancel out all your units, you should end up with an answer, and it comes out to be 0.060 liters. And that will give us 60. If we convert that back to milliliters, that'll give us 60.0 milliliters. And so the answer for this question is 60.0 milliliters. Okay, so hopefully you're kind of getting the idea now. This one again was a little bit different because of the diprotic nature of sulfuric acid. Okay, so we're going to do another practice problem. This is the third one. In this case, we have sodium hydroxide reacting with hydrochloric acid. So sodium hydroxide is a strong base. HCl is a strong acid. And if you mixed equal moles of these two, you would have what's called a neutralization reaction. The pH would be 7. And what you would have left over would be sodium chloride and water. Okay, but for the purposes of our video right now, we're simply using this as a titration example. So it's asking for how many mils of 0.0947 molar sodium hydroxide will be used for 20, so the volume of the acid is 21.4 milliliters of HCl was used. The concentration of the acid is given at 0.106 molar. The concentration of the base used is 0.0947 molar, and the volume of the base is what we're looking for. It's our X. So again, using the equation MaVa, moles of acid, equal MbVb, moles of base. We are looking for the volume of the base. So Vb, we'll solve for that. Vb is equal to MaVa over Mb. Molarity of the acid is 0.106 molar. Volume of the acid that was used. Now, we can leave this in milliliters because the other units, they're asking for the volume in milliliters. So 21.4 milliliters of the acid divided by the molarity of the base, which is 0.0947 molar. Molarities will cancel. We end up with milliliters, so those will be the units for the volume of the base. That's good. That's consistent with what we expect. And finally, Vb will come out to be equal to 23.6 milliliters of sodium hydroxide. So this is the answer for this titration calculation. It will take 23.6 milliliters of 0.947 molar sodium hydroxide to neutralize the 21.4 milliliters of 0.106 molar hydrochloric acid. And now this is the last practice problem we'll be doing. It is number 4. We simply start with lithium hydroxide. Lithium hydroxide. Okay, so it has the hydroxide ion in it, makes it a strong base. We are titrating it with hydrogen bromide. So we have HBr. Hydrogen bromide is a strong acid. And so again, this titration is what we would call a neutralization reaction. And so what we have then is, again, moles of acid equal moles of base. And the moles of the acid will be, we use 21.7 milliliters of the acid. You can write HBr times the molarity of the HBr, 0.0. If you want to see, you can write molarity in terms of moles per liter if you want to see how things cancel out. We use 26.4 milliliters of lithium hydroxide, the strong base. And the question is, what is the molarity of the molarity of the lithium hydroxide? So this is our unknown, our x. We're going to simply solve for that. So molarity equals of our sodium hydroxide will be equal to 21.7. If you look at this too now, liters of HBr cancel. This will be moles per liter. Liters would cancel if we had written this in terms of moles per liter. That would cancel, so we'd have molarity in the end. So we have 21.7 milliliters times 0.500 moles per liter. And that's divided by 26 decimal place here, 0.4 milliliters. Milliliters would be here. This would be molar. And if we want to check our units, milliliters would cancel out. You'd be left with molar, moles per liter as a unit. That's what we're looking for, so we're fine with that. And the answer will come out to be 0.411 molar lithium hydroxide. So the answer for this problem is 0.411 molar lithium hydroxide. And that pretty much wraps it up. Normally we would be doing all of this as a lab, but take a look at the video, practice some problems, and you should be good to go. Okay, so why do we care about some of these things? Well, acid-base chemistry is prevalent in our world. It's also present within our own bodies. Our bodies must be very tightly controlled as excuse me, as far as the pH goes. So if you take a quick look at this, we have a lot of acid in our stomachs. So we have a lot of acid in our stomachs here. Okay, so if you take a look at this picture, we have a lot of acid in our stomach, and we know that we can buy acid reducer, and in the form of Tums. We did an experiment like this during the stoichiometry unit where we neutralized some acid using Tums. So with the Tums, we were working with this is a weak base. This is a strong acid, which is in our stomach. So this is a weak base. And we used the weak base to neutralize the strong acid in our stomach, and it ended up producing the salt and water. And in this case, it also produced some CO2, so there would be some bubbles there when this process took place. So alternatively, you could have used something called milk of magnesia. That's magnesium hydroxide. That too, that's actually a strong base. And that too could be used to neutralize the hydrochloric acid in your stomach. And again, you would get some salt, which is an ionic compound, plus water. So this is also a neutralization reaction. So there are many instances of acid-base chemistry or buffering of your biological systems that keep you running well. So that's pretty much it. Let's see, there's a slide. And this is just another piece of the importance of acids within your body. And for those of you, and that's many of you who are athletes, lactic acid is the waste product that's built up in your tissue. And there's a process by which it's consumed. So what happens is when you don't have enough oxygen, and you end up with this feeling of feeling the burn, and that's actually when you're experiencing too much lactic acid in your muscles, because the reaction can't take place because not all of the reactants are there, and that's all shown in here. So this might be a little bit of review from biology class, but again, it's the citric acid cycle. And if you look, there's acid here and acid here. And so there's a lot of acid-based chemistry within our own bodies. All right, well, that actually wraps it up. That's the last slide. I hope this has been interesting. And I guess after this, we'll be working on a project, and then we'll end up finishing up the year. So take care, be well, and do some chemistry. All right.